Another day on section 5.7, and we're going to continue to try to work on some of these integration problems. And what we're going to find this time, if we look at problem number 1, I see 3 terms in the denominator. I see really there's just a 1 in this numerator. So what we're really integrating here is something that I can't split into multiple terms. And so plan B has always been, well, then do a u substitution. Well, if I said u was x squared plus 6x plus 15, then du is going to be 2x plus 6 multiplied by dx. And that 2x plus 6 is nowhere to be found. So I'd have to try to create it. So it looks like my u substitution is going to be a bad idea. So then the question becomes, all right, so last resort we learned in our last lesson was, what about the idea of this arcsine, arcsecant, arctangent thing? I don't have a square root in the problem. I see the x is being squared. Maybe that could be my u, but what do I do with this extra term over here? Well, what we see here is we've got a quadratic form of an equation in the denominator. And what's going to happen with these types of problems is if the arcsine or arcsecant or arctangent looks like it might be close, we might have to complete the square in order to get it into the form that works. And so that's exactly what's going to happen with this first one. We're going to look at this and we're going to say, I don't have a quantity being squared like I would need from our previous lessons. I don't have a quantity being squared. For example, I don't have a u that's being squared. And since I don't have that, I'm going to have to try to create it. So how do I create it? I create it by completing the square. So I'm going to start with my x squared plus 6x. I'm going to focus on just that much of it. If I was to complete the square, if I was to try to turn that blue thing into a quantity that would indeed factor to a perfect square, well, I'd take half of 6, which would be 3, and I'd square it, and that would be 9, and I'd add that on. And then I already had this plus 15 here. So then I'm going to, let's see, to balance this 9 that I added, I'm going to have to subtract a 9 in order to keep things equivalent. So if I do that, this first quantity, this x squared plus 6x plus 9, that's going to factor to an x plus 3 quantity squared. And then when I combine the positive 15 and negative 9, I'm going to have a plus 6. Well, if I rewrite this original integral then, using that information, let's see, so I've got dx on the top, or I've got 1 dx on the top, I guess we want to look at it that way. I've now got the quantity x plus 3 being squared plus a 6 in terms of my integral. Now, that looks a lot more like the form that we were using with what we had, and if I compare, this looks like it's going to be an arctangent because I have no square root and I have the 2 terms being added together. So we're going to say it looks like my u is going to be x plus 3 and my du is going to be dx, so I don't need to throw any extra things into the problem. And it looks like my a is going to be root 6 because that's what's being squared. So now go to your arctangent format. So if we clean this up, what do we have? Well, I've got, I know I start with 1 over a, and my a is my root 6 arctangent of my quantity u over a plus my c. What's my u? My u is my x plus 3, and my a is my root 6. So what's going to happen with some of these new problems is you're going to have issues where it might fit arcsine, it might fit arcsecant, it might fit arctangent, but we might have to complete the square in order to make it happen first. So second one. So problem number 2. Okay, again, multiple terms in the denominator. U substitution is going to require extra stuff that's not in the problem. No square root, so the only one that might work would be arctangent. So let's see what we can do. So we're going to start. This time we have a 2x squared minus an 8x plus 10. Now there's 2 ways we could go about doing this. One way would be you could factor a 2 out of the entire denominator. If that appeals, we could take a 2 out of this entire denominator and rewrite it as 2 quantity x squared minus 8x plus 10. The other way to do it, if you think back to your days in algebra, is to look at what you have. The 2x squared and the 8x is really what we're trying to change, and the 10 happens to be extra. So if you didn't want to factor a 2 out of the denominator and pull it out in front as a constant in the problem, actually maybe I should show what I'm saying here. we could take a 2 out of each of these terms, and we could rewrite this integral as 1/2 times the integral of dx on the top over x squared minus 4x plus 5. That would be a great way to go about handling this problem. And now complete the square with x squared minus 4x. That would absolutely work fine. In fact, you know what? Let's run with that. Let's see what we can do. So now take these two terms. Complete the square. X squared minus 4x. I need this thing to square, to turn into a perfect square. So half of 4 is 2. Squared is 4. We're going to add that on. We already had a plus 5. So now we're going to subtract to balance out our 4. So what I really have here when I rewrite my integral would be the integral with a green 1/2 out in front of it because of what I factored out. I have a dx on the top, and on the bottom I have x minus 2 quantity squared, x squared minus 4x plus 4, plus a 1, and that looks like an arctangent. It looks like in my arctangent it looks like u is going to be x minus 2. So du would be dx. I don't have to put anything in the problem. And it looks like a nice a there. It looks like a is going to be 1. So what do we have? We have a 1/2 of an arctangent, so 1 over a. So we're going to multiply by 1 over a. A is 1, so it didn't matter if we had that there or not. Arctangent of my quantity plus my c. What's my quantity? Numerator is x minus 2, denominator is a 1, so whether or not you wrote the denominator is kind of academic. If we clean all this up, we've got 1/2 arctangent of the quantity x minus 2 plus my c. So one of the things that you can do when you have to complete the squares, you can look for a constant that's common to all. If it's common to all, you can factor that thing out. And I think that's actually a pretty good way to go about handling that thing. Number 3. So number 3, now what we've really got an issue because this one's u substitution is not going to work because I'm going to need some extra terms that aren't there. This time, though, it looks like it's probably not an arctangent because of that square root that's there. And generally, when we complete the square, the x squared comes first. So I think what we should do with this one is we should rewrite it. So let's take this denominator. I'm going to work with just the 3x minus the x squared. I'm going to work with that first, and I'm going to manipulate it and play around with it. I'm going to start by taking that square root, and maybe I should bring a square root with. I'm going to rewrite this as negative x squared plus 3x. I'm taking that, I'm turning it around. Now, I wish the negative wasn't there. Let's factor the negative out inside this square root. So now I've got this negative that I'm factoring out. And if I factor that negative out inside my quantity, I now have an x squared minus a 3x. Okay, well, let's complete the square with that blue thing. So that blue thing, x squared minus 3x. Half of 3, 3/2, and it's better to use 3/2 than 1/2. It's just a little easier. Half of 3 is 3/2. Squared is 9/4. So we're adding 9/4 right here. But now in order to balance what I added, I really added a negative 9/4 here. I actually subtracted it. Negative times a positive 9/4 is negative 9/4. So now in order to balance that, I need to put a quantity out here that'll balance it out. Well, those two red things multiplied together are going to give you negative 9/4. So we'd better add 9/4 inside of this square root in order to balance this thing out. Well, if we rewrite the square root now, what I really have, if I change the order, is I have a 9/4, and interestingly enough, it's already written in red, minus the quantity x minus 3/2 squared. So that's my new integral. I now just took it. I took what was in the denominator. I did what I do as far as completing the square, and I made things balance. So integral dx in the numerator, square root in the denominator, and that square root is 9/4 minus the quantity x minus 3/2 quantity squared, and now that looks like it's going to fit. Well, let's see, the a comes first, so this looks like an arc sine. So my arc sine, a is going to be 3/2, that's what's being squared. U is going to be x minus 3/2, gosh, having trouble writing, sorry. X minus 3/2. So du is the same thing as dx. Don't need to throw anything extra into the problem. So now this is an arc sine. Arc sine doesn't require anything in the front. And let's see, arc sine of my u over my a plus my c. U is x minus 3/2. Denominator is a, which is 3/2. I've got fractions inside of fractions. Quick way to fix that, let's multiply the top and bottom by a 2. If we multiply the top and the bottom by a 2, then what we've got is we've got arc sine of the quantity that's being, a quantity being divided, plus my c, that quantity. 2 times x minus 3/2 would be 2x minus 3, and on the bottom 2 times 3/2 is going to be a 3. So there's how it goes with a square root. Square roots, you're going to have signs that are going to mess you up, like that red negative sign that you see at the far left. But just remember, reverse your terms, take out your negative, and complete your square, and just make sure whatever you have, make sure is equivalent. All right, last one, so number 4. So number 4, I guess I want to leave this one on the screen so you can see it. Number 4, the denominator looks really similar to number 3. But what's tricky this time is we've got 2x minus 9 on the top. So my first thought when I see a problem like this, if I did a u substitution, I wonder if it would work. So let's play for a second. Let's say that I made u equal to 4x minus x squared. If I did that, du would be 4 minus 2x. And then I'd have to multiply all that by a dx. So you know what I want to do? I'm gonna rewrite this this du. And how about if I call it negative 2x plus 4 times dx, or that's really the same thing as the opposite of the quantity 2x minus 4. Now I write it that way because as I'm looking at this thing, what do I have in the problem? In the problem, I don't have a 2x minus 4, but I do have the 2x. Wouldn't it be nice if instead of having a 9, I had a 4? Well, here's what we're going to do. What if we said, instead of calling this thing a 9, what if we said that's not a 9, this is minus, whoops, sorry, minus, let's see, wait a minute, 4 plus 5 would be the same thing as 9. So if I rewrote that integral, I could call this thing the integral of 2x minus 4 in the numerator, and then I could have a minus 5 over there to balance it out. So if you just look at just the top of my fraction, I distributed the negative, that's why this 5 has a negative sign on it. If I wanted to, I could call this first integral the square root of 4x minus x squared dx with a 2x minus 4 on the top. Now, the tricky thing is, what happens with the minus 5? Well, the minus 5, that 5 is over the top of a square root of 4x minus x squared. We just created 2 integrals. The first integral, we're going to use everything that's over here. The second integral, and the reason I left this stuff on the screen, the second integral is going to look a lot like the one that we did in number 3. Because in the second integral, the u substitution isn't going to work, but I bet if I complete the square a lot like I did in problem number 3, this is an integral I'm going to be able to do. So what I've got here is I've kind of got a little creative u substitution worked in here in the middle. We know that this first integral, when we go and we rewrite it, we're going to need to throw in a negative into the problem, and we're going to end up integrating the square root of u on the bottom, or u to the negative 1/2 du. So there's your first integral. So we've already done all the work just because of what we thought might work. We've already got that one ready to go. Well, the second one, what are we going to have to do? Second one, we're going to have to do a little scratch work here probably, because this looks like a completing of the square one. I'm thinking maybe arc sine because of the way number 3 looks. So let's start with the square root. So I've got my square root here. I'm going to do a little scratch work. So my square root, let's see, negative x squared plus 4x square root negative quantity. Whoops, I want to stop that quantity. X squared minus 4x when I take the negative out. Half of 4 is 2 squared plus 4. Now let's do the red thing again. I have a negative times a positive 4, which means I really have a negative 4 that I created. So out here I'm going to have to add on 4 in order to make this thing balance. So what do I really have inside the square root? I've really got the quantity 4 minus x minus 2 quantity squared. And that looks like we are set up to do an arc sine now. So what I've really got is I've got two integrals here. I've got this integral that has a negative 5. You know what I'm going to do with that negative 5? I'm going to put that negative 5 in front of this thing as a constant because we don't really need it. And then I've got 1 over the square root of 4 minus quantity x minus 2 squared as a result of my completing of the square part. Well, this first integral I know I can do. This first integral is going to end up to be, let's see, add 1 to the power, it's going to be u to the 1/2. Divide by the new power means we're going to be multiplying by 2, and we've got a negative there. Minus 5, and then what do we have this time? This is an arc sine. So a is going to be 2. U is going to be x minus 2. du is going to be dx. No need to throw anything extra into the problem. So what I should probably do is I should probably move this down a little bit so we can see it. So we've got negative 2 u to the 1/2 minus 5 times my arc sine of x minus 2 divided by 2 quantity plus my c. Now once you're done putting your u back in, so how about negative 2 times the root of 4x minus x squared minus 5 arc sine of x minus 2 over 2 plus my c. So that is a pretty complex antiderivative. One of the more complex ones you'll do all year. And we ended up having to create a second term there. Got a little creative because of what we noticed with the u substitution. So we tried u substitution, it didn't work. We got creative right here with this 4 plus 5, and we ran with what we came up with as a result.